Let me further illustrate this expression x to k for cases when k is 2. Consider the following differential equation. Y second minus 6y derivative plus 9y is equal to 7 times e to 3x. First we write the homogeneous equation, which is y second minus 6y derivative plus 9y is equal to 0. Then we write the characteristic equation, lambda squared minus 6 lambda plus 9 is 0. Well, this is equal to lambda minus 3 squared that is 0. And this has two real roots which are the same. So this is the double root or root with multiplicity 2. Note that this equation is not the same as the equation lambda 3 is 0. This has solution lambda is 3, this has solution lambda is 3. For our purposes, the multiplicity is important. This equation has the root lambda is 3 with multiplicity 1. This equation has the same root but with multiplicity 2. Also, the difference will be quite visible when we plot the left-hand side. The function x minus 3 or lambda minus 3 looks like that. And it is equal to 0 for lambda is equal to 3. One simple root. While the function x minus 3 square root that or lambda minus 3 square root that is a quadratic function. So the graph is not a straight line, the graph is a parabola having the minimum at the point 3. So you see two completely different pictures, right? And the multiplicity of the root, the root being double root, is seen from this picture that not just that the function value is equal to 0 at 3, but also the derivative is equal to 0. If you take the function x minus 3 squared and if you differentiate, you have 2 times x minus 3, which is also equal to 0 at 3. If you take the function x minus 3 and differentiate that, this is not 0. You see, the slope here is non-zero, while the slope of the tangent here is equal to 0. So, similar equations, but for our purposes, when we count the multiplicity of the solutions, different. Okay, so this is not important for us today, and we have these two roots that correspond to two functions. y1 is e to 3x, and y2 is x times e to 3x. So the general solution to this homogeneous equation is c1y1 plus c2y2, which is c1 e to 3x plus c2 times x times e to 3x. So that was for the homogeneous equation. And now let's have a look at the non-homogeneous equation. Well, the wrong way would be to assume the solution in the form a e to 3x. But this is not good because e to 3x solves the homogeneous equation. Even if you multiply by x, this is still not good because x e to 3x also solves the homogeneous equation. So we must multiply by x once again to arrive at x squared times e to 3x. And this is the correct form, this is the correct expression for the solution. Alternatively, we can build the number alpha, which is a plus ib, where I and b are the two coefficients from the right hand side. A is the coefficient at x in the exponent, 3. B is the coefficient at x in the arguments of sine and cosine. If there is no sine and cosine, here, then b is 0. Then alpha is a 3 plus 0i, which is just a real value 3. And now we look whether this number, alpha is 3, is or is not in the list of solutions of the characteristic equation. Yes, it is here. And it is here twice. This is namely a double root. So k is 2. So we must multiply by x to k, which means we must multiply by x squared. Oh, k is 2. Sorry. Well, and if we know the form of the solution, well, we can find the value of the coefficient a. We prepare the first derivative, which will be derivative of x squared is 2x, plus derivative of e to 3x is 3. e to 3x, and ax squared is there. And the second derivative is, well, we can factor out, okay, we can do it this way. So derivative of x is 1 plus derivative of e to 3x is 3 times this, so this is 6a x e to 3x. So that was for the first term. And now the second. 3a times x squared derivative, which is 2x. So we have 6a x e to 3x plus 9a x squared e to 3x. So we take y and y derivative and y second, and we substitute it here, and we compare with what is on the right. So we start with y second, which is 2a e to 3x. Then x is multiplied by a and e to 3x, and 6 plus 6 is 12. A x e to 3x. And then we have 9 times ax squared. So this is for y second. Minus 6 times y derivative. Minus 6 times this. Minus 12. A x e to 3x. Minus 18. ax squared e to 3x. Plus 9y plus 9ax squared e to 3x. And that should be equal to 7 e to 3x. Well, x squared is here with coefficient now. Yeah. 9 plus 9 minus 18 is 0. Then next to 1, 12 plus 12 minus. And 2a e to 3x is 7 e to 3x. So 2a is 7. So a is 7.5. And what we have? A, we have this y, which is the particular solution of the homogeneous equation, 7.5 x squared e to 3x. And then we take the general solution of the homogeneous equation, and we can write the general solution of the non-homogeneous as the particular solution of the non-homogeneous plus general solution of the homogeneous, which is 7.5 x squared e to 3x plus c1 e to 3x plus c2 x e to 3x. So this is the general solution of the non-homogeneous equation. We could save some time and some writing if we omit e to 3x, because this factor, you see, is in each term. So we could make a convention that we will divide by e to 3x, and then the writing would be a little shorter. So the main idea is when what we want to assume as the solution of the non-homogeneous equation, if it solves already the homogeneous equation, no sense to consider this to solve the non-homogeneous if it solves the homogeneous and the result is 0. So we must multiply by x. If multiplying by x does not help, we must multiply by x squared. Alternatively, we build a number alpha, and we look whether this value alpha, 3 in this case, is or is not in the list of roots of the characteristic equation. In this case, it turns out that 3 is a double root of this equation, and if it is a double root, then we must consider k is 2, and we must multiply by x squared.